Nope.
Hi everyone, we are Team 35 and today we're going to present our project about the Turbo Trike. Our advisor for this project is Dr. Samuel Landsberger and we're sponsored by John Wieland and GridAlternatives.
Hi, I'm Loren. I'm the Team 1 lead, which covers suspension, autobraking, the roll cage, and the road legal modifications. I focused personally on the suspension.
I'm Jihane and I'm the Team 2 lead, which covers steering, solar charging, and regenerative braking. I work primarily on the steering.
My name is Jairo Martinez, and I focus primarily on suspension and scale modeling.
My name is Wesley Aquino. I primarily focus on the roll cage.
My name is Martin, and I will be focusing on auto braking.
Hi, my name is Iron. I'll be focusing on roll cage and street legal design.
Hello, my name is Hernan Reyes, and I'll be focused on steering and the frame.
My name is Bonilla, and I'll be focusing on solar charging.
Oh, and my name is Dillon, and I'll be focusing on regenerative braking and safety features.
Before we begin introducing our project, we first want to show why the project exists in the first place, specifically the global impact, which will lead into our objectives and constraints. Then we'll go into the previous generation of trike and introduce our two different new turbo trike models for this project, which incorporates an improved suspension, steering, and roll cages. We'll also describe auto braking, regenerative braking, solar assist, road legal requirements, lateral acceleration, rollover prevention, as well as show scale models. Phase 1 was completed as of last semester, which covered the general plan of what the trike could look like, along with plans for scale modeling, Phase 2 deals with agreeing on a final trike design, improvement plans, fabrication of scale models, perform testing on the scale models, and prepare for the Expo. The limitations set for meetings and general hands-on work challenged the team to focus less on manufacturing, as the team had little to no access to the trike itself, and instead focus on simulations and numerical analysis, leading up to giving finished schematics for the upcoming senior design year. The team narrowed down the modified designs to two general options, and fabrication of scale models had begun. However, due to limited meeting times and scheduling conflicts, testing was not able to be performed.
Our objectives for the projects are to improve on the existing electric turbo trike for daily applications. We sought to maintain safe driving dynamics at speeds up to 45 miles per hour, improve power efficiency by implementing regenerative braking, increasing driving range by 30 miles through solar panels while always maintaining the rider's safety and increasing its accessibility.
So let's begin by understanding the impact of a traditional vehicle on our planet. Most cars today travel by using internal combustion engines that burn gasoline or other fossil fuels, which contributes to air pollution and releasing CO2 into the atmosphere. To combat this, numerous initiatives to promote electric vehicles have been put into place, and the sector is expanding every day. Recently, President Biden committed $174 billion toward electric vehicle incentives. These efforts prove that designing and building an electric three-wheeled vehicle can only benefit nature and our fight against global warming. Electric three-wheelers have the advantage of lower fuel costs and almost zero emissions. However, it is important to ensure the safety and comfort of the rider. Therefore, it is required to conduct a careful design, kinematic analysis, and testing of our trike.
The original TurboTrike began life as a KMX Colt recumbent tricycle before being outfitted with a Kelly Controls KVL controller and a 48-volt, 30-kilowatt brushless DC motor. It is powered by two lithium iron phosphate batteries. The controller currently limits the batteries to half power, but the vehicle is still quick. There are numerous economic issues which will be addressed with our design, and at higher speeds, the trike shows some stability issues and understeer when cornering.
Here is a video of a team member driving the trike. As you can see from this, the turning radius is quite large, especially for a vehicle of this size. The lack of front suspension also makes going over bumps and ruts quite jarring. The braking distance is quite long as well, even at these low speeds, and the brakes operate independently of the left and right front wheels, with no rear brake. Also, the steering handles invade the driver's space, and the twist grip throttle is prone to turning during steering. All of these issues are addressed in our modifications to the trike.
Due to the lockdown, it was not possible to go into the labs and construct our designs ourselves. While unfortunate, it did allow us time to instead invest our time in exploring different designs. The two teams took a fork in the road and designed trikes with different goals. Additionally, the importance of having physical designs to work with was not ignored. We decided to construct scale models of our designs to have a tangible version of our work. To begin, we reviewed the original trike requirements and found what the common area was for both designs, as well as what were things that could be different. This roadmap shows how each branch came to be and what the ideas were behind each one. Model A prioritized minimal modification, quick driver controls, and a roll cage that had to be designed for this particular frame. Model B prioritized overall comfort and accessibility, as well as precise driver controls. Due to the major differences, this also required a specific roll cage. The common ground was made up of safety features and modern improvements. This included solar power, auto braking, rollover prevention, and all the necessary features to make this trike street legal. After finishing all the design work, the teams would produce small 1/4-inch scale models that would represent the two designs. From this, the team would construct a decision matrix and pick which design should be fabricated by the following team.
The first design for modifying the original TurboTrike was Model A, pictured here. The goal of Model A was to be as conservative as possible about modifications, while meeting or exceeding the design requirements. The design attempts to make as few large modifications to the original vehicle as possible, keeping as many original components and frame sections as possible. The design sought to improve the handling of the trike and make it drivable and comfortable at speeds of up to 45 miles per hour. To do this, a suspension, steering wheel, foot pedals, roll cage, and other modifications were made. The existing trike has no suspension for the front wheels, and as a result it rides very rough, and bumps in the road can affect stability. To fix this, numerous suspension designs were investigated, and each had its own benefits and drawbacks. 4 main designs were considered. The double wishbone design, on the top left, consists of 2 A-arms that move together. This was the most conventional design, which is found in most vehicles, but it was moderately complex and difficult to implement on the relatively small TurboTrike frame. The middle image is the suspension from a BMW Isetta, a microcar from the 1950s, in the middle. It utilized a Dubonnet suspension, which is an outboard trailing arm design. It was fairly compact and is immune to the effects of bump steer, which is where suspension travel influences the steering angle, but unfortunately, it consisted of a number of special cast parts that would be very difficult to replicate. We also investigated an in-wheel compressible spoke design, which is simple, takes up next to no space, and is immune to bump steer as well. But it is inefficient by nature, as the spokes must compress and decompress with every revolution, and it offers minimal suspension travel as well. Here is a model of the Isetta suspension that I made in a dynamic simulation program. Note that the wheel travels on the arm connected to the orange pivot on the right. The suspension operates at the green pivot behind, and the whole assembly rotates on the blue pivot to steer. The intricacy of this assembly is why we opted against using it. Here are the 4 main suspension designs we considered, with their key qualities weighted by importance, these being how much real estate the design requires, how difficult to fabricate and integrate it is, and how badly is it affected by bump steer. As you can see, the compressible spoke design was the clear winner, but upon realizing the inherent inefficiency of the design, the transverse leaf became the next best choice. After considering all of those options and their qualities, the suspension selected for Model A was the transverse leaf arrangement. So a leaf spring is very cheap and very sturdy, and is relatively simple to integrate onto the existing trike. It is also very short vertically, which is important since the driver's legs must be able to pass over the leaf while seated. Additionally, a leaf spring suspension is easy to adjust should the trike experience greater load. A purchasable leaf pack, as seen in the bottom right, comes with many leaves, which can be added and removed to change the spring rate. This transverse design transverse leaf design may seem unusual, but it can be famously found in the Chevrolet Corvette from the C4 to the C7, if you're familiar with those vehicle designations. Here, the suspension is pictured on the trike with the leaf spring in red in the top right, between the two swing arms in blue, and connecting them are the green shackles. This design is quite cheap as well, with the two black shackles in the center and the leaf pack coming in well under $100. So to determine how many leaves are necessary, the deflection equation for a leaf spring stack was applied. The goal of the leaf was to flatten out when load is applied, causing the wheels to obtain neutral or negative camber. The leaf becomes flat when the shackle holes are displaced by 6.3 centimeters. An average rider was assumed to be about 96 kilograms, and with that, the center of gravity is a bit forward of the center of the wheelbase. Splitting the load between the tires, the load at a front wheel comes out to about 1,000 newtons. Plugging in the values results in a force to deflect the spring of about 1,030 newtons, which is almost exactly the required amount. The strain is also well within the plastic region of the steel under loading, and additionally, should the rider want an improved spring rate or to change the ride height, additional leaves may be added, and the center hold-down plate can be lifted or lowered.
So one of the most important components in our trike is the steering system. So what is the purpose of a steering system? The steering system, along with the suspension system, allows the driver to easily and safely control the vehicle's direction while driving. Compared to the first generation steering system that had no suspension, we plan to implement a suspension system to our trike. The steering system consists of a collection of components and linkages, which allows any vehicle, whether it's a car, bicycle, or motorcycle, to follow a desired path. Most vehicle steering systems are composed of steering linkages, a steering column, a steering gear, and a steering wheel.
Turbo Trike initially was designed with handlebars that were placed side to side from the driver. Steering angles were limited and would range from 15 to 25 degrees depending on the driver's body width. This design was found to be awkward and produced tire scrub when cornering. The overall objective in terms of steering was to reduce tire scrub due to the lack of Ackerman steering, easier to steer by incorporating a steering wheel, comfort, which will focus on sitting and handling position. Lastly, safety was also considered in terms of turning radius and rollover.
Like we said before, the steering is a system of components, linkages that help control the direction of the vehicle. So we want to give a little bit of information about the evolution of the steering system until today. Automobile was invented more than 100 years ago. As an important part of automobile, steering system was also created with the automobile evolution. However, in the early times, automobiles were steered with the tiller, which is basically a lever. It was not until 1898 that the steering wheels were introduced as a standard feature in cars. At the start, steering wheels had a simple design, wooden circles directly connected to the wheel axis. They were extremely hard to turn, especially at low speeds. Until 1920, the first power steering system was invented, and that made the control of the direction of a vehicle much easier for the driver, and which we find in today's cars. For our project, we've studied different types of steering mechanisms in order to understand how they work, how to implement them, and if they would be a good fit for our trike. We considered two types of steering systems, the rack and pinion steering and the pitman arm steering, along with a specific steering geometry, the Ackerman steering.
Ackerman principle is a common steering geometry that is used to reduce the tire scrub when cornering by making the inside wheel turn on a tighter radius than the outer wheel. To achieve a smooth path, the front wheel axis should intersect at an instantaneous center to the rear wheel axis, so that the front wheels create a concentric path.
So for Model A, we focused more on maximizing minimal modification to the existing model and minimize overall cost. Thus, this matrix was constructed to decide which steering to choose for Model A. Here are the two main designs we considered, which is the pitman arm steering and the rack and pinion, with their key qualities weighted by importance. As you can see, the pitman arm seems to be the winner. The pitman arm. It consists of moving the steering rack according to how you steer. The steering rack is connected to the tie rods, which are connected to the steering arms. The tie rods are the connection from your steering system to your wheels. So here's our model of the Pitman arm steering, including the leaf spring suspension. And as you can notice, we added a clamp shaft with screw stoppers to the model in order for our steering wheel to have some limitations while turning, simply because without a stopper, our steering wheel would keep turning, resulting in our tires colliding with the frame. So that is the reason why we decided to have a steering stopper. A pitman slot was also added to the steering to accommodate the suspension and reduce bump steer. Moving on to the next slide. In this case, we did the turning radius calculations of the pitman arm steering with the stopper included. And following the parameters that we find on the right, it resulted in having a turning radius of 5.69 meters. This slide compares the steering ratio of different types of vehicles, from the regular cars to fast cars, go-kart, and finally our Turbo Trike with the pitman arm steering and rack and pinion steering. So the steering ratio basically corresponds to the steering wheel rotation angle to the steer angle at the tire wheel. A lower steering ratio would mean that the steering wheel turns less to get the tires turning. However, it will make turning the steering wheel harder, which is the reason why larger and heavier vehicles will have a higher steering ratio to make the steering wheel easier to turn. While for normal and lighter cars, the wheels are easier to turn, so there's no need to have a high steering ratio.
Roll cage is engineered construction frame built to protect passengers from rollover and collision. In order to make a roll cage, me and Wesley were looking into similar the vehicles as our Turbo Trike, and we found Polaris Slingshot and a Ricci Moto FUV. After looking at their test crashes and design, we came up with our designs. Now Wesley will continue with the roll cage that he designed.
A simple design for Model A was constructed with the goal of maximizing safety and ease of assembly while also minimizing the cost. This was done with the use of triangulation, also known as stagulation. Triangulation focuses on simple geometric shapes, where one diagonal member across a 4-bar linkage maximizes rigidity while focusing on using the least amount of material possible. Here to the left is an example of what proper triangulation looks like. We're using the same dimension/material of a 4-bar linkage as a base, a diagonal line connecting corner to corner, minimum deflection when compared to a diagonal line connecting from a corner to the midpoint of the bottom of the bar. The benefits of Model A are a low center of gravity due to the lowered seating position, relatively low weight of 300 kilograms. This simplicity allows for the least amount of modification to the previous generation of the model, further leading to a low cost for overall assembly. Here are a few materials under question to be used on the roll cage alone. While this analysis could be used for the entire model, in this case, it's specifically tailored for the roll cage. The 7075 T6 aluminum does indeed have the highest tensile strength. However, it does not allow for torsional loads to be absorbed correctly without perhaps injuring the driver. In the presentation, it will be shown why ASI 4130, otherwise known as chromoly, was used with the decision matrix. Next, a cost analysis was done on the 5 materials. Certain assumptions were made to properly gauge a minimum price for assembly. One, that all materials were bought using raw stock, opposing from stock tubing to just give to the machinist. 2, that a general rate of 1.5 to 2 times the cost for working with of a machinist working with aluminum as compared to other materials, and 3, of a general base rate of $20 an hour for any machinist. It is important to note that while aluminum has a significantly lighter weight and raw stock would not be too expensive, machinist rates would quickly add up. Finally, here you can see a decision matrix was performed in order to focus on which material would be the best to use, with a range from 1 to 3 points: cost, weight, safety, weldability, and machining. cost of labor, and the cost of labor was accounted for. When weighing each score, it becomes evident that while ASI 4130 or Kamali received the low score based on its mass, safety is ideal as it has a similar tensile strength to that of 7075 T6 aluminum, which, as if you remember, it had the highest tensile strength overall. However, ease of labor is really the reason why it went to this material, as it allows for the machinist the easiest time for welding, as tube stock is easy to bend. Having the material also be annealed would lend it to having an improved ductility. So we had an objective of 45 miles per hour, or roughly 20 meters per second. However, we designed around a crash zone of 0.6 meters, or roughly 24 inches, and a weight of 300 kilograms with the driver. With these constraints, we were able to calculate for a reasonable deceleration of impact at max velocity and a time of collision from start to finish. Using the impulse equations, impact force, and Newton's laws of motion, we calculated the energy absorbed by the crash zone, as well as force felt from the impact. From our constraints and design conditions, we found our impact force to be 100 kilonewtons, our deceleration to be 333 meters per second squared, or roughly 34 Gs, and finally a value of 60 kilojoules for energy absorption. To the right, you can see how the impact force would affect the roll cage at full frontal collision. As you can see, with the use of center section of the trike where the roll cage is mounted under the trike, the roll cage would deform, the roll cage will deform the least where the driver's legs and body is located, with little deformation at the head region. This deflection could be further counteracted with a simple helmet in regards to remaining as safe as possible. Now we will look at what would happen if the trike would experience complete rollover. Here we accounted for the mass being 300 kilograms with the driver, acceleration due to gravity, which gives us a force of 3 kilonewtons, acting at the top of the trike, assuming its complete rollover. Overall, the roll cage will hold and protect the driver. However, deformation would be less if tubing was used, had thinner walls and larger outside diameter, which would improve the overall rigidity of the trike, of the roll cage.
The second design was Model B, shown here fully equipped with its rack and pinion steering, independent front and rear suspension, as well as its front mount bumper assembly, roll cage, and outrigger. Here we see how the design criteria for Model B were determined. Model B aimed to transform the current trike into something completely new, with a primary focus on comfort and controlled behavior. This model would change drastically from the current version of the trike. From the previous version of the trike. First, to maximize comfort, we wanted to increase the cabin space to 914 millimeters and design a suspension that would have dampening and would allow for at least 51 millimeters of travel. For driver controls, the goal was to have a steering system with a 3-to-1 ratio that would not be overly sensitive to prevent possible accidents. This steering system should be in a position comfortable to the driver, and the pedals to control the vehicle should be mounted as far away as possible in order to increase legroom. Driver protection would design a roll cage that is both visually appealing and also does not compromise on safety. It would have a 603 millimeter energy absorption zone in the front that would absorb all the impact and not buckle in on the driver cabin, and would also allow enough room to mount the solar panels. To maximize comfort, the current trike was inspected, and it was found that the main portion of the frame could be used to provide enough space for a comfortable seating position. But the way the seat was mounted, only about 27 inches were usable. This also made the driver's feet dangle over the front axle, and we wanted to avoid this for fear of frontal impact resulting in catastrophic injury to the leg area. The rear swing arm was 21 inches long, which seemed excessively long, but was required due to the physical size of the batteries. The solution was to relocate the batteries to the side of the frame using cages that will also serve to make a floorboard and strengthen the original frame. Since the rear swing arm would no longer carry the batteries, it could be shortened down to 15 inches, helping to keep the overall length of the trike at a minimum. In the front, the damp suspension is supported by offset members that are attached to the battery cages. The suspension allows for 51 millimeters of travel at the wheel end. Other more complex suspensions were considered, but preference was given to these type of spring damper setups because they are easy to source. Since the damper is mounted at a short distance away from the wheel, the ride will actually be firm. And although firm ride is usually less comfortable, it provides better suspension control. Ideally, this position of the damper would be experimented with to find the most comfortable ride. To verify that the new suspension geometry would work with the planned shock absorber, a simple analysis was done under static conditions and under an event of 51 millimeters of vertical deflection. This proved that the shock absorber would only deflect 1 millimeter in the event of 51 millimeters of travel at the end of the tire. Since the currently planned shock absorber supports 101 millimeters of travel, that is well within our range. The previous trike has one single damper mounted at the center, at the rear. However, Model B uses two dampers to avoid torsion at the shock mounts because the rear swing arm has been modified to locate the dampers at the sides instead of at the center. This suspension had an assumed travel of 51 millimeters as well. The dual dampers provide better ride control and help avoid sag when loaded.
Rack and pinion is a type of steering system that involves a set of gears which converts rotational motion to linear motion. This steering can be found in cars, minivans, and small SUVs. The previous model had a quick-turn go-kart steering of 1:1 ratio, which can pose a danger if the wheels turn too quickly. Model B aimed to improve the steering control, so we proposed a rack and pinion steering system. This design has a 3:1 ratio, which means less effort and more control on the steering wheel compared to the go-kart steering. Here we would demonstrate the turning radius of Model B when we assume a 4-meter radius. From the diagram, you can see that the inner wheel is much greater than the outer wheel, and with the given angles from the assumption, we can calculate for the actual turning radius, which was determined to be 4 meters. This is a comparison table between pitman arm and rack and pinion steering to help decide which model is best in terms of complexity, durability, vibration, weight, cost, and materials used.
In the previous design, the control pedals would have to hang over the front bar of the frame. With Model B, the pedals can be mounted within the cabin and far away from the driver. This is because the driver will be raised from the floor about 10 inches and thus allowing the feet to be in a more comfortable and outstretched position. The pedals are mounted to the floorboard and also are up against the roll cage, meaning that they are about 914 millimeters away from the driver's back.
Our roll cage objectives were safety, accessibility, comfort, and aesthetics. Model B has 15 centimeters removed from the rear swing arm. Use those extra 15 centimeters to add crumple zone in front of the trike. Battery cages are attached to the frame all at the same level. Then laterally support between both cages added strength to design in the event of a lateral impact. The roll cage B adds support for rollover conditions uses the front 15 centimeter provided by shortening of the rear swing arm. Material used to build the roll cage is 1015 ASI. Dimensions of the bar were 24 times 2 millimeters. Energy absorbed are 303 millimeters times 441 millimeters. Roll cage weighs 48 kilograms, which adds the total weight of the TurboTrike 344 kilograms. We are using the same formulas which Wesley introduced earlier, and after doing the calculations, we got acceleration to be at 67 Gs and came to a conclusion that we are going to need a bumper for driver safety. After adding the bumper, our distance increased to 0.6 meters, and we used the same formulas from the slides earlier. After doing the calculations, we got the lower acceleration at 33.94 Gs, which means the driver safety increased with the bumper. Roll cage benefits are a larger surface on the top of the roll cage in order to mount the solar panels, easily to weld, and the higher seat position that allows the driver better visibility, and the last is comfort.
Components that can be used in both TurboTrike models are auto braking, solar panels, regenerative braking, and street legal. First gen trike is not very safe nor efficient. That is why we decided to add some components that will improve safety and efficiency. The first gen trike did not have enough sensors incorporated to the trike. It did not have lights or turn signals, solar panels, or regenerative braking. That is why we decided to include in the second gen trike auto braking, front and back lights and turning signals, solar panels, and regenerative braking, making it safe to drive and more efficient than the first gen TurboTrike. So when determining which sensor to use, we took in consideration certain criteria: the communications protocol, maximum range, sampling rate per second, water resistant IP67, and cost. We compared 3 different sensors: the LiDAR Light V3, the RP LiDAR S1, and finally the TS03 long distance LiDAR. The TS03 long distance LiDAR module was our top choice for the implementation of the auto braking, keeping us under budget at $229. The LiDAR can measure up to 180 meters and a frequency of 10 kilohertz, making it ideal for our second generation trike. It is connected to the Arduino Uno board through UART, and most importantly, it has anti-shock, anti-vibration, and can operate up to 60 degrees Celsius without any issues. Calculating the stopping force to the left is the formula and the process shown of how we can determine the stopping force if the initial velocity is 30 meters per second square. As you can see, we will need 1,436 approximately newtons to bring the trike to a complete stop, estimating the mass of the trike to be 200 kilograms. From this calculation, we can create the code that will determine when the trike activates the auto braking system. The figure in the slide shows the wiring diagram of the auto braking system. This diagram will hopefully make it easier for anyone that will be working on the trike in the future. Also, we will be providing the code in the PDR with step-by-step instructions on each line of code. Since we are not allowed to work in the actual trike, I decided to test the auto braking system at home by adding an LED light and a DC brushless motor and an ESC. I use a potentiometer to control the throttle and an LCD to display the distance of any object ahead. This is the schematic for the previous slide. This can be very useful for the next team that will be working on the TurboTrike, since it is able to clearly display every connection and can have a better understanding of how everything works. It will also be added in the PDR so the next team can refer to. So in the video, you can see the distance being displayed on the LCD screen and the strength of the signal. For testing reasons, I configured the code to activate the DC motor if the distance captured by the LiDAR sensor is greater than 2 feet. Now, if it is less than 2 feet, then the DC motor will stop. That's when the regenerative braking will activate. Also, the LED will activate if the distance is under 2 feet.
In many modern cars, there are a multitude of sensors placed all throughout the vehicle for various different safety features. That may include blind stop monitoring, lane keep assist, auto cruise control, as well as auto braking. The sensors for these systems are all throughout the car, some being on the sides, the rear view mirror, and then the front and rear bumper. Of course, many of the auto braking sensors are near the front. An early design put the TFO3 sensor just under the top part of the roll cage, and a smaller TF Mini could sit in the bumper. This would allow the larger sensor to be centered and safe from impact. The bottom of the part would be on a hinge and could be used to aim the sensor into a correct position. Some issues arose from this design and forced a change in its location. First off, you could see in the image, it would not have the clearest view of the road, as part of the roll cage would interfere with its imaging. Another problem is, depending on the angle at which it was set, it would not be very effective at certain ranges. So the decision to put both sensors into the front bumper was made. The TF Mini could sit inside of the rubber bumper and be off-censored to allow for the bumper to take the full impact in a front-end collision. The TFO3 sensor was moved to a small cage just behind and under the bumper. This would keep it out of the way of a minor crash and allow it to have the best view in front of the trike. In order to protect these sensors, the bumper would need to be able to withstand an impact of 10 miles per hour with minimal deflection. It was found the bumper would experience 15,000 newtons in this kind of impact. The bumper will be made out of aluminum 661 because of its lightweight, and it's commonly used as a structural part of bumpers in modern cars. The front part will be made of natural rubber because of its high tensile strength and resistance to fatigue. Running a stress analysis on this bumper with a 1500 newton force at the front shows it will have minimal deflection and keep both sensors safe. Another aspect being added to both trike models is regenerative braking. A traditional combustion engine, the vehicle's primary mode of deceleration is friction. When it wants to come to a stop, the brake pads place against the rotor, preventing from spinning. With this kind of system, all of the car's momentum and kinetic energy is wasted through heat, but with regenerative braking, it is capable of recapturing some of that energy and feeding it back to the batteries. When the driver presses on the brakes of an electric or hybrid vehicle, the electric motor runs in reverse and works as a generator. Now next, the TurboTrike is outfitted with a brushless DC motor at the rear, and also known as a VLDC. Inside of the VLDC motor, there are stator teeth either all around the shaft or in this diagram, around the outside. A current runs through the coils of the teeth on opposite sides and induces an electromagnetic field. The permanent magnet on the drive shaft is attracted towards that field, and then the next set of teeth is activated, and the magnet continues to chase the changing magnetic field. To provide more torque and speed, the motor can switch the polarity of the field as the magnet passes to push it along, as it's also pulled from the other. A Hall's effect sensor is used to know the position of the magnet so the teeth can be activated at the right moments. When regenerative braking is used, a set of stator teeth activate and attempt to hold it in place. The moment of the vehicle wants to keep the rotor spinning. As the permanent magnet spins between the coils, it induces the current back into the motor where it can be fed to the batteries. There are a couple different parameters we can use to evaluate how well regenerative braking systems work, both being the efficiency and effectiveness. Efficiency refers to how well regenerative braking captures lost energy. In other words, how much of the kinetic energy gets back into the battery. It can be found from this equation where electric energy recouped into the battery over the difference of kinetic energy, where EK is the voltage of the batteries, IT is the current of the batteries, and RT is the charging resistance. Effectiveness refers to how large of an impact it will make on the driving dynamics. It ends up being much harder to calculate as it depends on a large number of factors. Driving conditions have a large factor on the effectiveness. In the city, where a car is stopping going more often, the effectiveness will be higher than when driving on a highway. Terrain is another factor. Going downhill, where the brakes can be used the majority of the time and then recoup more energy than on flat ground or going uphill. Probably the largest impact of effectiveness is vehicle size. The larger a vehicle will have more mass and more momentum and be able to get more energy out of stopping. But a heavier vehicle will negatively affect the range when its motor is running. So because of this, there's a balance that needs to be met when designing to maximize a vehicle's range. Regenerative brakes are great on a car to drive around town and could only be used using regenerative brakes are great and could be used around town only using those, but it might not provide enough stopping power in the event of emergency. So all cars with this feature have normal friction brakes as well. In cars with both systems, it requires cooperation between both regenerative brakes and the friction brakes. The process of getting these two systems to work together is torque blending. Two possible control strategies to accomplish this are parallel and serial regenerative braking. A parallel regenerative braking system is based on a combination of both braking systems working in tandem simultaneously. In this system, as the brake is pressed, both regen and friction brakes increase along the length of the pedal's motion. And this system has an effectiveness of about 9 to 18%. Serial regenerative braking uses an integrated control system that allows the regenerative brakes to fully apply before the friction brakes activate and allows for a more consistent pedal feel. The serial braking system requires a brake-by-wire system, and there are some worries that this kind of system could fail. So right now, cars produced with this have a backup system that activates hydraulic brakes for those situations. This system will see higher effectiveness of between 15 and 30%. These charts illustrate how the delivered brake torque varies along the length of the pedal in each system. The yellow region represents the regenerative braking, while the red represents friction brakes. The compression region refers to the regeneration when the accelerator is released. In a parallel system, we see how when the regenerative braking reaches their maximum capabilities, continuing to push the pedal result in a smaller increase of the desired braking torque. Although in the parallel system, or the series system, the braking torque increases is constant all the way through. This design matrix shows the considerations that we were made and the weight given to each. The complexity of the serial braking system made it less likely as an option, although it saw slightly better effectiveness. This allows us to keep, we will use the parallel braking system, and this will allow us to keep the brakes that are there on the trike now. The trike now has a vertical handlebars with the throttle on the right side and individual brakes for left and right wheel. We will switch to the pedal system for a more user-friendly interface that everyone should be familiar with. However, the pedals will be operated by the left and right foot independently, similar to a go-kart. Measure the rider's input potentiometers will be placed at the base of the pedals and attached to their axles. Small boxes will be used to protect the sensors from the rider stepping on them. Underneath the foot plate, we will use tensile hook springs to bring the pedals back to their neutral position. On the brake pedal, we will use the cable-driven system and attach it through the spring so it can be applied as the brake is pushed. When we can adjust the slack of these cables to activate the friction brakes slightly after the pedal has traveled some to give it slightly improved effectiveness.
Solar panels. The harnessing of solar energy has been around for a very long time. Some of the very first solar panels were created in the 19th century, but it wasn't until 1959 that The current silicon solar cells that are still used today only had 4% of efficiency compared to the 20% that we have today. We live in a time where people are becoming more environmentally conscious and are aware of their carbon emissions. As demand for renewable energy increases, solar panels are becoming a viable option for people who want to reduce their emission because panels are becoming more efficient and more affordable. As more auto manufacturers are making the switch to electric vehicles, many companies plan to phase out combustion engines completely from the lineup by 2035 and only offering EVs as their options. As of right now, battery technology still has room for improvement, and companies are already trying to make the most use out of the batteries by adding solar panels to add range. Some current examples are, for example, we have Toyota, who partnered with Sharp, creating solar cells that are 40% more efficient, and they claim to add 40 miles to the current Prius model. Then we have Tesla with the Cybertruck that already has an impressive 500-mile range. They want to add, since the truck is so big, they want to add solar panels on the back of the truck to add an extra 15 miles of range. And then we also have many startups like Aptera and the Lightyear One, whose sole focus is just the main source of charging is solar panels. And for Aptera, their proud point is that their never charge technology can add 40 miles of range just by parking outside, and allows for the Aptera to have a 1,000-mile range due to not having to plug in to charge as much. And we have the Lightyear One, a company from the Netherlands, who the Lightyear One is a larger vehicle, so it has a larger size for more solar cells. And they also claim to have a 40-mile charge a day, while also using mostly cells to power their hub wheels like we do in the trike. And these are just a few companies that are messing around with this technology, and there's more companies that are likely to follow. So the last group has blessed us with two lithium iron phosphate batteries that are perfect for solar charging. These are tough batteries, and they are becoming the battery of choice for people building off-the-grid solar systems because they are way more efficient than lead acid. Each battery pack has a voltage of 36 volts and a capacity of 50 amp hours. Since they are in parallel, the voltage stays the same, but the capacity increases for a total capacity of 100 amp hours. So with that requirement, the solar system must be capable of charging 36-volt batteries. So the demand for renewable energy is up. Although people continue to add solar panels to their cities, to their homes and cities, adding more types of renewable energy to create more power for the grid, most charging still comes from the grid, and most of it comes from fossil fuels, causing the grid to produce an ample amount of CO2 into the atmosphere. The goal is to reduce our reliance on the grid, which will lower our carbon footprint by adding solar panels to the trike, which will allow us to drive longer without having to plug in to charge. And with that information, on average, most people drive 30 miles a day. And currently with the estimated range, and that's including all the weight from the roll cages and the components added on, the estimated payload range is around 90 miles of range. So with a quick calculation of energy consumption, coming from a full charge to empty, our energy consumption is about 40 watt hours per mile. So using that number, the system needs to create 1,200 watt hours to make up for the 30 miles driven. As for connections, the criteria used was pretty simple. A series connection will allow for greater voltages more than 36 volts to charge the batteries, while also requiring less adapters, which will cut cost because we don't have to buy more wires or more adapters. As for the type of solar panel, there are two kinds. We have monocrystalline and polycrystalline. The difference is that the monocrystalline panels are essentially just one single silicon crystal for each cell, while the polycrystalline panels are basically each wafer is melted, a whole bunch of melted crystals to create one. The best option here would be the monocrystalline panels because they're about 6% more efficient than the polycrystalline, which is a huge number when it comes to solar panels. Also, the monocrystalline panels have rigid and flexible options, and they also come in smaller sizes that can make the most use of our trike area. So when we come to the panels, when given the option between flexible or rigid, flexible panels were the best option due to their bendability and are a lot lighter than rigid panels. The mass of the panels should not affect the battery efficiency due to being about 4 pounds each. So with the three 12-volt panels in a series, the systems will create 300 watts an hour at peak performance and will create the needed 200 hours in just 4 hours. The charge controller here, as you can see in the schematic, and the disconnect that are close to the battery will allow for more control of the system and will allow us to turn off the charge controller will help avoid overcharging from the panels to the batteries, and the disconnect or fuse will give us more control of the system in case there was an emergency. And this slide is just having flexible panels just leaves to limitless arrangements, allowing for more complete designs that I will leave for the next team to decide. So after this little bit of information, are the $500 worth of panels worth it? The system has an ability of creating 511 kilowatt hours of energy a year. Currently, SoCal Edison charges 22 cents a kilowatt. So for comparison, it will cost 38 cents a day to produce the same amount of energy from the panels using the grid. Yearly peak production from the panels will save us about $112 compared to the cost of $138 using the grid. So with that price, the panels will eventually pay for themselves after about 5 years, more or less, probably more, while reducing our carbon emission of about 0.362 metric tons of CO2. Adding this system will reduce our need for the grid and while also achieving the goal of 30 miles of added range.
In order to make the TurboTrike state legal, we need headlights, taillights, turn signal, horn, mirrors, and speedometer. In order to do those parts, I need to make a few systems. The first one is the headlight signal system. I started designing the system from the battery, which is already installed on the bike. On the battery, we have positive and negative poles. Negative will have 2 wires. One needs to be connected to the ground and the other one needs to be connected to the both headlights. For the positive pole, wire will go into the light switch. On the light switch, there will be 2 options for the high or low beam. They will be connected with 2 different wires like shown on the picture. Next picture is the turn signal system, which is similar to the previous one. Instead of the wires going into the light switch, they will be connected to the flasher. The flasher will have an option to set how fast do we want the blinker to go. From the flasher, there will be only 1 wire going into the turn signal lever. From then we will have 1 wire for the left side and 1 for the other side of the vehicle. Last system is the taillight system, which is similar as the other system. The only additional is the brake switch, which is located below the pedal. Once the driver presses the pedal, the taillight will turn on. The most important part about the system is that they're designed for 12 volts and the battery is designed for 36. In order to make the system work, we will need a converter like it's shown in the picture. Seatbelt is not mandatory to get a bike street legal, but we added it in order for the driver's safety. Once we have the proper modification, the bike needs the inspection. After it passes the inspection, the next step is going to be title and registration. Once we do all of that, the next step is going to be insurance, and the last step is the license plate.
Since we are working on a 3-wheeled vehicle, it is more susceptible to rollover than one with 4. Having the roll cage is great to protect the rider when it flips, but we want it to only occur in the most extreme of cases. The image here shows a simplified 3-wheel vehicle making a right-hand turn. The reaction force is that the tires act normal to the weight. The centrifugal force acts lateral on the trike and is denoted by AYW, where AY is the lateral acceleration. The friction forces act towards the center of the turn at each wheel. It is likely in most cases that the wheels will lose traction and slide before tipping, so we will assume that the tires maintain their traction throughout the turn and focus on the tipping moments and the normal forces at the wheel. This will give us a higher lateral acceleration than what the trike is likely to experience under normal conditions, and designing for this threshold will make it safer in the end product. When we add up the moments about the center line on the road and at the base of the rear wheel along its axis, we get the 2-moment equations to the right. If we solve for AY, we will find the maximum lateral acceleration in terms of g-force. Now we will apply that equation to both of our trike models and find their respective max accelerations. We find that Model A has a much lower center of gravity and a longer wheelbase, can experience much higher lateral acceleration at 0.97 Gs compared to the Model B's 0.6 Gs. This result in Model A being able to make a turn at 45 miles per hour with a radius of 26 meters smaller than that of Model B. Although these outrigger wheels could be used on Trike A by attaching to the roll cage, the spring we will use will be designed within the context of Model B because it will need a much greater force to counter out the tipping. It will be capable of preventing the tip in Model B, it will be more than capable in Model A. This image shows how the outrigger wheels will be attached at the back of the trike. The outrigger wheels will be placed 0.52 meters from the center and sit roughly 0.06 meters from the ground. This design will allow for a maximum of 15 degrees of lean about and 0.038 meters of travel at the spring. If we were to go around the corner at 45 miles per hour with a turning radius of 8 meters smaller than our R critical, the trike will be experiencing 2,300 newtons of centripetal force. The simplified diagram shows the moment on our trike when it has tilted 15 degrees and the outrigger wheels are acting against the tipping moment. The reaction forces at the wheels are R1 for the front, R3 for the rear, and R2 at the outrigger wheel. FC is the centrifugal force acting at the center of mass, and our OR is the outrigger distance. The notation of the distances from the center of mass to the wheels are the same as in the previous example. Like in the previous analysis, we will also assume no sliding at the wheels and focus strictly on a rollover case. We sum up the moments about the same axes as well in that diagram, which in this case is at R3 about the x-axis and at R3 about the z-axis. We plug in our values we find the force needed to counter out the tipping moment at the outrigger wheels is 680 newtons. We want to know what spring constant is needed to safely push back the trike back onto its wheels. Hooke's law, F equals displacement times the spring constant, allows us to find the necessary constant. We find that this will need to be 18,000 newtons per meter. The current space given for the trike will not allow for a spring of this strength, so the next step will be to thicken the bars of the outrigger and connect the spring to the bar closer to the rear wheel, allowing for larger space for the spring.
So, because constructing the actual trike in the makerspace was impossible, the teams created remote-controlled scale models to test the key design elements. The models test the designs of the actual trike suspension, steering, solar charging, and drivetrain. The bulk of the model's frame and mounting components were produced using 3D printing. PLA filament is both low-cost and sturdy, and allows for strong and inexpensive parts. Even stronger PLA Plus filament was used for components under heavier loads. The trikes used 11.1-volt lithium polymer batteries hooked up through electronic speed controllers to brushless DC outrunner motors. RC Model A is shown to the left, utilizing leaf spring suspension, and Model B is to the right, with coil spring suspension.
Summarizing, Model A requires minimal modification, meaning low cost and time to construct. It also has a very low center of gravity, thus reducing the risk of rollover. While ergonomics in this model are a concern, the roll cage does give a handhold, making ingress and egress much easier than before. Model B requires extensive modification with a substantial time requirement, and it also has a high center of gravity, and thus increasing the chance of tipping. Despite this, Model B does have excellent ergonomics, safer and superior steering to Model A, and a safer crash structure. These considerations and others were placed into a decision matrix to determine which trike was ultimately the most viable option. The greatest emphasis was placed on simplicity, which takes into consideration the amount of work needed to modify the trike. If the complexity is too great, a student team would not be able to construct it themselves in a given time. The next most important consideration is the safety of the trike. Model B's more substantial crash structure gives it a larger crumple zone to reduce the acceleration in the event of an accident. Both trikes add considerable weight to the original TurboTrike, but Trike A adds 100 pounds less than Trike B. A very important consideration is the likelihood of the trike tipping over. One of the key modifications of Model B was raising the seating position, and while this does help with a number of ergonomic features, it also raises the center of gravity of the trike, thus increasing the chances of tip over compared to Model A. The philosophy behind Model A of sticking as close to the original design as possible results in a much lower overall cost compared to Model B. Considering the ergonomics of the vehicle, Model A received a low score because of its low seating position, which makes getting in and out of the car a bigger issue. The seating position can also be very uncomfortable over extended periods of time. Steering ratio was a deciding factor as well, because although quick steering can be beneficial in low-weight vehicles, if the vehicle is moving at a high enough speed, it can become dangerous. Since this vehicle has a limited capacity, range, and top speed, it also wouldn't make sense for it to be bigger than other vehicles on the road that can move at greater distances and have greater passenger capacities, as well as higher top speeds. For this, we added length as a category, scoring higher if a vehicle had a shorter length. The totals were close, but due to the weightings of each criteria, Trike A proved to be the most viable option to be built.
Many of us wouldn't be sitting here today if we hadn't been shown how cool STEM is by people working in it. This is why we must emphasize the importance of STEM to help create the next generation of engineers. The TurboTrike laboratory also serves as a demonstration of the applications of math and science to real-world problems. We have assembled some problems for high schoolers based on the challenges we faced while designing the trike. We used the top equation to find the lateral g-force that would tip our trike, but using the second equation, it can also be done for four wheels. You could use this to find at what lateral g-force would flip any one vehicle. SUVs are particularly susceptible to rollover, so here's one you can try. The new Nissan Pathfinder has a track width of 75.7 inches and a height with center of gravity about 50 inches.
Like the equations used to calculate the G's felt on the system by a full frontal collision in earlier slides, I'd like to challenge young students and future car enthusiasts to figure out why your parents don't want you to drive that 500 horsepower sports car and instead wish for you to drive a Toyota Corolla instead in regards to safety.
Thank you for taking the time to listen to our presentation, and a big thank you to Dr. Landsberger, our advisor, for his tremendous help and patience through the senior design process. We look forward to your questions.